fibers. So I would hand over to Dr. Preetham Hayat. Sir, please continue.
Okay, so am I audible to all of you?
Yes, sir.
Okay, I'm all right. I'm just sharing my screen to all the participants. Just a minute. Yeah, just a minute.
Hello.
Yeah, just a minute. I'm sharing my screen to all the participants.
Yes, sir. Yes, sir.
It's hanging, so it's taking a little bit time. So my computer screen is visible to all of you.
Yes, sir.
So okay. So good afternoon to all the respected dignitaries and my colleague Snehanshu Nath. Thank you for invitation to give me the chance to deliver my lecture. This is Dr. Preetham Hayat. I am from NIT Silchar. I have completed my doctorate and masters from NIT Silchar in the year 2020 and 2015 respectively. My research domain is structural damage assessment, and also I have worked on fiber reinforced concrete. So now I'm going to present my research on experimental investigation of hybrid fiber reinforced self-compacting beam column joint sub-assemblies under cyclic load. So uh, this is the paper that I have recently published in structured elsewhere that I am going to present to all the participants. So here okay, so let's start the introduction. Nowadays, due to the huge construction, the emission of carbon dioxide is a problem, and it is the cause of global warming. We can see in the figure, due to the construction, the manufacture of the cement and the demand of the cement is increasing by many folds nowadays. So therefore, there is a threat to the environment that causes the global warming. To reduce the demand of the cement, we can go the replacement of cement that can be replaced by the existing fibers. There is two types of fiber are available. First one is natural fiber. Second one is artificial fiber. Now, why I am introducing the fiber? Because the fiber is not only replacing the cement requirement in the concrete, but also it offers the resistance of crack, increases the strength in the concrete specimen, and also it gives stiffness ductility property in the concrete. Therefore, we can use the available fibers, natural or artificial, whatever, and we can replace the cement. Somewhat it can reduce the emission of carbon dioxide in the environment. So in this way, we can save our environment, also enhance the performance of the concrete. In natural fiber, we have jute fiber, coconut fiber, banana fiber, textile fiber, which are commonly being used in construction and also laboratory in different educational institutions. And there are so many artificial fibers are available. That is glass fiber, rectan fiber, steel fiber, nylon fiber. Okay. So in this study, we have seen that several researchers are using different kinds of fiber in their concrete. Due to the high tensile strength and ductile property, the fibers are being mixed with the concrete to enhance the performance, overall performance. So the fibers reinforced concrete beam column joint can enhance the entire stability of any structure. The application of different fibers has been increased in many fields that we are going to see in the literature review. You can see the previous published paper by the previous researchers. There we can see the researchers how they are using different fibers in their research. Here we can see the list of researchers and their paper have been published in the journals. In the year 2018, Poa LA et al. They have used the fibers. We can see the ratio of joint depth to diameter of the reinforcing bar in the beam was developed. Okay, so further we can see the other researcher Sahavas from et al. In the year is not mentioned. So they have done the carbon fiber reinforced concrete polymer, and the carbon fiber reinforced concrete polymer has been used as a sheet to shift the failure from column to beam. That means these researchers have manufactured the carbon fiber sheet, and it is used to minimize the damage to shift the damage from column to beam. That is desirable in construction sector. Further, we can see the Ridwan Rahman Samir et al. They have used also carbon fiber to minimize the damage and also the deterioration of the concrete. It is published in ASC journal, and we can see the epoxy coated steel bar enhanced joint shear strength, ductility, dissipated hysteretic energy, stiffness by 21%, 93%, 54%, and 30% respectively. So we can see further.
Hello, sir.
Yes, sir. Yeah, madam.
Sir, you are on the literature review slide only, sir. We are not able to see the other slides.
Okay, right. Yeah, and now it can be visible. Hello. Now can it be
Yes, sir.
visible? Hello.
Sir, it is visible now.
Okay. So now several researchers are doing research with the existing natural and artificial fiber, such as steel fiber, carbon fiber, polypropylene fiber are being used to enhance the overall performance of the concrete in terms of stiffness, degradation, energy dissipation, damage index. Okay. So we have reviewed so many literatures, and from the existing literature we have came to a conclusion that the steel fiber is quite efficient to strengthen the structure, and also it offers the crack resistance property to the concrete. Okay. The screen is visible to all of you.
Yes, sir.
Okay. So now from the literature we have observed the following points that I am going to highlight. The steel fiber is quite efficient to strengthen the concrete, and also it is significant crack resistant. Therefore, we can use the steel fiber. That is one part of the literature review. The another part of the literature review is uh, apart from steel fiber, the available natural fiber offers low cost strengthening and ductility property to the concrete. Okay. So now, apart from steel fiber, we can also use the natural fiber that is available at low cost, and also it gives the strengthening and ductility property to the concrete. Okay. Now, what is the significance of this current research? We can see the different natural fibers are available, such as jute fiber, coconut fiber, that is also called coir fiber, banana fiber. Among all the available fiber, Erica leaf sheath fiber has become a popular nowadays. Okay, we can see the Erica leaf sheath is being used to prepare the plates, and that is also biodegradable in nature, and it can also be used as a fiber in concrete that offers the crack resistance property, and it is also available at a low cost. Okay, so if we are interested to construct low cost construction, we can go for Erica leaf sheath fiber. Here we can see the figure of Erica leaf sheath fiber. Here first the Erica leaf is collected from the forest and or from any garden, and they are dried, or naturally they are dried, and they are also cut into pieces at certain dimension, and they are mixed in the concrete. How the procedure will be done one by one, I'll discuss now. So this is the significance, and also it offers the tensile strength at low cost, because the Erica leaf sheath is cheaply available in rural and urban area that can also be used. That also reduce the demand of the steel fiber. Okay. Beside this, Erica leaf sheath fiber is naturally available, and it reduces the emission of carbon dioxide in the environment, unlike steel fiber. Okay. Now we are going to start the methodology. In this research, I have used Erica leaf sheath fiber, steel fiber, ordinary Portland cement with grade 43, coarse and fine aggregate, and Chryso fluid optima K15, which has been used as super plasticizer. This super plasticizer not only uh, enhance the workability, but also it resist the segregation of concrete. Okay, sometimes you can see the concrete segregate from the coarse aggregate. If we use this Chryso fluid optima K15, it will resist the segregation between concrete mortar from the coarse aggregate. This is very useful super plasticizer. Next, the test specimen has been prepared fast in the laboratory. In this research, I have prepared total 13 number of beam column joint that had been casted in the laboratory. So those specimens are cast. We have casted the control specimen, reinforced concrete beam column joint. That is fast specimen. It has no fiber. Next, we have casted the helical lip sheath fiber, reinforced concrete beam column joint. It is termed as ALS FRCBC 1%, 2%, 3%, 4%. This is the percentage of fiber have been varied to find out the optimum percentage. Okay. Similarly, for steel fiber and also steel helical lip sheath hybrid fiber. So these are the 13 beam column joint have been casted and they had been tested in laboratory. Okay. So before the casting, we need to design the beam column joint. Okay. So the design of beam column joint is very important, and it has been designed as per IS 13920-2016 and associated with Indian Concrete Journal. The beam column joint is an integral part of a building, reinforced concrete building, and during the earthquake, we have seen that due to stress reversal effect, the beam column joint is subjected to huge amount of shear and bending moment through multiple axes. Therefore, it should be designed as per our Coral Permission 13920-2016 and Indian Concrete Journal. There is a documentary given by the IIT Kanpur, and I have also used that documentary. It is published in Indian Concrete Journal. In this equation, we can see the shear in column, which is equal to the 1.4% of moment in beam to the center to center distance in the column. These two Coral provision is most important. One is shear in column should be equal to the 1.4 times to the ratio of MH to HST, and moment in column to moment in beam should be greater than or equals to 1.4 times. These two provision is most important, and it has been followed during the design of beam column joint. MC is the moment in column and MB is the moment in beam. Okay. You can see the entire paper that I have clearly explained how the design should be done associated with the documentary offered by the IIT Kanpur and IS 13920-2016. Here we can see the detailing of the reinforcement in beam column joint and also the cross section of the beam and column. Okay, so the beam column joint especially the joint region is the most vulnerable region because it is subjected to stress reversal during the earthquake. Therefore, it should be designed in special provision even in 13920-2016. The joint region is most vulnerable. Therefore, here I have provided the stirrups at lesser spacing, and the which is 6 mm bar at the rate 30 mm center to center, and the rest of the part, the stirrups are provided stirrups are provided at 6 mm bar at the rate 50 mm center to center. So this is very important during the design of beam column joint. We can see the columns are reinforced with 6 number of bar, 6 mm 6 number of bar, and the beam is reinforced with 2 number of 8 mm bar at top and bottom. Okay, and the dimension of the beam column is also shown in the figure. Next, the cross section we can see here. The beam is designed as 120 by 150. 6 mm sit-ups are used, and the column is also maintained at the same dimension 120 into 150 with 6 mm sit-ups. Okay. The instrument setup and the loading techniques is shown in this figure. Uh, the actuator is available at the structural engineering laboratory at NIT Silchar. That actuator diagram is shown in this figure. It is a schematic diagram. First, we can see the basement of the actuator and the actuator support. From the support, the hydraulic actuator is hanging and it is giving the load on the beam at the tip of the beam. The different parts of the specimen is shown in this figure. Here, the column is placed horizontally and the beam is placed vertically to apply the load at the tip of the beam. Okay, and here the hydraulic jack is provided to apply the axial 10% axial load on the column, which is realistic in nature. The 10% axial load, that is 100 kilonewton load, is applied on the column, and in between this, the proving ring is placed to measure the load given by the hydraulic jack to the column. So this is the instrumental setup that had been done at NIT Silchar laboratory. Now the loading history you can see here in this figure. The investigation has been performed with 1 mm initial amplitude and 1 mm increment amplitude till the failure. Okay, you can see the constantly loops. That means first we have applied 1 mm, 3 loops, that is tension and compression. This is the cyclic load. So 1 mm displacement is applied with 3 loops. Next 2 mm displacement is applied for 3 loops. Next 3 mm, 4 mm. In this way, we have increased the displacement till the complete failure of the specimen. Okay. Next, the details of the test specimen we have already explained in the figure. Also, we can see here the high capacity 1000 kilonewton servo hydraulic actuator is used in this experiment. The actuator can apply 90 mm displacement in both positive and negative direction. That is, it can apply tension and compression to the specimen, and also it can apply 1000 kilonewton load. That is the maximum capacity of the actuator. The column is placed horizontally and the beam is placed vertically to apply the load at the tip of the beam. That I already explained in the figure, previous figure. Next, the column is subjected to 10% gross load, that is 100 kilonewton, to explain the realistic scenario. In reality, we see by default the column is subjected to the axial load. When the axial load is applied to the column, it increases the load carrying capacity of the column. Therefore, to simulate the realistic scenario in the laboratory, we have applied the 10% axial load on the column. Next, the hydraulic jack is placed on the column to apply the load, and to measure the load, we also have used the proving ring. Through the proving ring, we have measured the axial load, that is 100 kilonewton. These are the crack pattern. We can see the beam column joint, which is subjected to cyclic load, and eventually the load is increased from 1 mm to 1 mm, 2 mm till its failure. We can see here the crack pattern. First, the specimens are uncracked and they are after casting, they are cured for 28 days. After curing, they are painted with white lime to make the crack easily visible. Okay, so this painting is very important for better visibility of the cracks developed. So we can see in the figure A, B, C, D, E, the specimen how they are cracked after applying the load. Here we can see the steel fiber reinforced concrete beam column joint. In the first figure, figure A, it is control specimen where there is no any fibers are mixed with the concrete. Next figure B, 1% steel fiber is used. In figure C, D, and E, 2%, 3%, and 4% steel fiber has been incorporated. After applying the load pattern we can see here, and this kind of crack has been developed after gradually increasing the load. Okay, from here we can see the fast crack and the ultimate crack. The fast crack reveals the yield strength of the specimen, and finally when it fails, that final crack reveals the ultimate carrying capacity of the specimen. We'll see what is the ultimate carrying capacity in the next following figure. Here we can see the crack pattern of the Erica leaf sheath fiber beam column joint for 1%, 2%, 3%, 4% fiber. And here we can see the steel Erica hybrid fiber. That means here we have mixed steel fiber and Erica leaf sheath fiber at 50% steel fiber and 50% Erica leaf sheath fiber, and that total 50% is mixed at percentage of 1%, 2%, 3%, and 4% in the figure A, B, C, D, representing the steel Erica hybrid fiber reinforced concrete beam column joint. So this is the three variation that we have tested in the laboratory, and here we can see the crack pattern. Next, the reinforced concrete beam column joint specimens failed before the fiber reinforced concrete specimen. It is obvious because the fiber offers the resistance against crack, and also it enhances the strength and ductility property of the concrete. It is very obvious. Next, the yield point of the FRC is much more higher with compared to the reinforced concrete beam column joint, resulting in fiber reinforced concrete experiencing X pattern crack later than reinforced concrete beam column joint that is not incorporated with fiber. We can see the X pattern cracks is easily visible in the specimen. We can see the X pattern cracks is developed. The load carrying capacity has also been increased by 5 to 23% for Erica leaf sheath fiber, 5 to 27% for steel fiber, and 2 to 33% for hybrid fiber. We can see the crack pattern. In the previous figure we have seen the crack pattern. Now we will see the hysteretic behavior of the joints. Okay, hysteretic behavior means when the joints are subjected to load in positive and negative direction, how they are behaving. We can see here. This is the first figure represent the hysteretic behavior of reinforced concrete beam column joint. In figure B, C, D, E represent the Erica leaf sheath fiber, 1% Erica leaf sheath fiber, 2% Erica leaf sheath fiber, 3%, and 4% Erica leaf sheath fiber, and the hysteretic behavior you can see. Now, what reveals the figure? What reveals the hysteretic behavior of reinforced concrete beam column joint, Erica leaf sheath fiber beam column joint, steel fiber leaf sheath fiber beam column joint, and steel Erica leaf sheath hybrid fiber beam column joint have been plotted in the following figure. In this figure, the loading unloading pattern we have observed. The maximum load carrying capacity and minimum load carrying capacity we will see in the next table. The maximum load carrying capacity is 8.5 kilonewton occurred at 36.55 mm displacement. On the other hand, we can see the FRC, that is without fiber, experience fiber reinforced concrete experience higher load carrying capacity due to extra resistance capacity offered by the fiber with compared to the simple reinforced concrete beam column joint without fiber. Okay. These are the hysteretic behavior of the specimens. This is for steel fiber reinforced concrete beam column joint with different percentage of fiber. Figure A, B, C, D represents 1% steel fiber, 2%, 3%, and 4% steel fiber. And next, this is the steel aerial hybrid reinforced concrete beam column joint with 1%, 2%, 3%, and 4%. Further, we can see the envelope curve. Envelope curve represents the peak points of the hysteretic curves. Here you can see the hysteretic curve. If we add the hysteretic curve, the peak point of the hysteretic curve, we will get the envelope curve that has been plotted in the figure. It will explain, it will reveal the maximum load carrying capacity of the specimen for all the specimen. You can see the maximum load carrying capacity of Erica leaf sheath fiber reinforced concrete 3%, showing the maximum load carrying capacity. Okay, at 3%, the maximum load carrying capacity occurs. Okay, next you can see the envelope curve. This is for 1%, this is for 2%, this is 3%, this is 4%. Okay, so maximum load carrying capacity for each and every cases you can see it is occurring at 3% fiber. Okay, you can see the maximum load carrying capacity, yield point, and peak load. What is the peak load? We can see in this table for different specimens. For ALS 1%, 2%, 3%, 4%. Steel fiber reinforced concrete beam column joint 1 to 3, 4%, and steel aerial hybrid fiber reinforced concrete beam column joint for different percentage of fiber. Okay, and previously we also have seen the reinforced concrete beam column joint without fiber. So in all cases, we have observed that the maximum load carrying capacity is occurring in case of steel fiber reinforced concrete beam column joint. After that, hybrid fiber reinforced concrete beam column joint showing the higher load carrying capacity. Then aerial leaf sheath fiber is showing the higher lower peak load. Okay, so if we see which specimen gives the maximum peak load, we can see the only the steel fiber reinforced concrete specimen is showing the maximum, then hybrid fiber, then aerial leaf sheath fiber. Okay, the performance can also be explained by the stiffness degradation. We can see the previously the performance can be explained by load carrying capacity, maximum load carrying capacity, the hysteretic behavior of the structure, the envelope curve of the specimens. Now we are going to explain the stiffness degradation. Stiffness is gradually decreasing with the displacement. When we are increasing the displacement, the stiffness will automatically decreases due to the damage. Okay, so from the figure A, B, C, D, we can see the stiffness degradation, and for all the cases we can see steel fiber reinforced concrete, steel hybrid fiber reinforced concrete, and aerial leaf sheath reinforced concrete. For all cases, we can see the 3% is the optimum percent where the uh, maximum strength is occurring, and also maximum stiffness is also occurring at 3%. These are the specimen name and their corresponding initial stiffness we can see in this table. Next, we will explain the performance of the specimen in terms of energy dissipation. This energy dissipation is calculated in Excel with the help of the MATLAB, and we can see the area covered by the hysteretic loop that have been shown in this figure. The area covered by the hysteretic loop shows the energy dissipation. Those total energy dissipation have been plotted in this figure, and they are varying with different percentage of fiber. This is for in x-axis I have plotted cumulative dissipated hysteretic energy. In y-axis it is plotted displacement. With displacement, the energy dissipation is increasing. So we can see the maximum energy dissipated at 3% for all cases. Here we can see this is the comparison of energy dissipation. The first figure explains the eddy lipstick fiber. Next figure, that is B, explains the steel fiber reinforced concrete beam column joint, and this figure explains the hybrid fiber reinforced concrete beam column joint. The steel eddy hybrid fiber beam column joint. For all cases, we can see the 3% is the optimum. In these 3%, it is dissipating maximum energy. When it release the maximum energy, the damage will be more. Okay. So we can conclude now after the results. We can conclude that in this study we have casted total 30 number of specimen. First, we have casted one reinforced concrete beam column joint without fiber, that is called control specimen. Next, 4 specimen for eddy lipstick hybrid fiber, 4 specimen for steel fiber reinforced concrete beam column joint, and next steel eddy lipstick hybrid fiber reinforced beam column joint for 1%, 2%, 3%, 4%. Okay. Next, the performance of the joints have been explained in terms of energy dissipation, stiffness degradation by various aspects. First, we'll see the eddy lipstick fiber reinforced concrete beam column joint and steel fiber reinforced concrete beam column joint have outstanding performance against bending, crack propagation in beam column joints. Okay. The overall seismic performance of beam column joint have been increased significantly due to incorporation of the fiber. For both the cases, eddy lipstick and steel fiber, the performance of the joint have increased significantly. Next, we can see the increase of load carrying capacity for both, for all eddy lipstick fiber, steel fiber, reinforced concrete beam column joint, and hybrid fiber increased by 3%. Okay, the load carrying capacity have increased 5 to 23% for eddy lipstick fiber, 5 to 27% for steel fiber, with compared to the conventional reinforced concrete beam column joint. The performance of steel fiber reinforced concrete beam column joint is better than eddy lipstick fiber beam column joint. This is obvious because the strength of steel fiber is higher than eddy lipstick fiber, which is natural. Next, we can see the stiffness of steel fiber reinforced concrete beam column joint is better with compared to conventional reinforced concrete beam column joint, and eddy lipstick fiber reinforced concrete beam column joint, it increased 25 to 107% for ALS fiber and 19 to 81% for steel fiber. So these are the comparison is done in terms of stiffness, ductility, energy dissipation capacity. Okay. So in terms of energy dissipation capacity also we can compare, and the energy dissipation capacity increased by 18 to 68% for ALS fiber and 12 to 87% for steel fiber. The ductility property also can reveal the performance of the specimen. It leads a better seismic performance of the structure. Okay, the incorporation of both steel fiber and ALS fiber have enhanced the seismic performance of the joint by increasing the ductility by 9 to 32% for ALS fiber and 11 to 41% for steel fiber. That is far better than the contour specimen RCBCJ. Here you can see the fiber resists the crack propagation and deflection drift of the beam column joint. Beside this, it can also enhance the ductility and shear resistance capacity due to incorporation of the steel fiber and ALS fiber, Erica Lipschitz fiber. In case of hybrid, that is steel Erica Lipschitz reinforced concrete beam column joint, it also shows the optimum result from both performance and economical point of view. This point is very important because in hybrid, I have mixed steel fiber and Erica Lipschitz fiber. Now the steel fiber is costly and it is not available in all the area in India. But Erica Lipschitz fiber is freely available or it is available at cheap cost in both rural and urban area. So in case of rural area, if there is no such steel fiber is available or due to the economical point of view, the Erica Lipschitz fiber can be better choice, better than the reinforced concrete beam column joint without fiber. So where people cannot afford the steel fiber, they can also use freely available Erica Lipschitz fiber with concrete to enhance the performance. Further, if the steel fiber is available and people can afford, then they can use steel fiber reinforced concrete beam column joint. And if we consider performance and economical point of view, we can use steel Erica Lipschitz hybrid fiber reinforced concrete beam column joint. So this is the one of the great aspect from this research. Now anybody can ask any question regarding this research and I'll try to answer. And in future, if you are interested to do such kind of research, you are always welcome and you are always welcome to be associated with me. I'll help you with my level best.
Hello.
Yes, madam.
Hello.
Yes, madam.
Yeah, students, anyone has any questions for sir? You can raise your hand so that I can allow you. Anybody has questions?
Anybody
You
can
can
ask.
raise your hand or write in the
and
chat
I
box.
The thing is that when you are going to start your research, I don't know whether you are pursuing MTech or PhD. So experimental work is always great, and it will have more weightage. Okay, so always go for experimental work, and always try to go for green building, which is very much acceptable by government of India. This kind of research is promoted by the government nowadays. Green building in the sense which reduce the demand of the cementitious material and also reduce the emission of the carbon dioxide. So it will be very helpful to the environment, the society for long term. Now anybody can ask any questions regarding this research. I'll try to help you.
Students can write in the chat box or you can raise your hand, please. I think, sir, they don't have any questions right now.
Okay.
So if they have any, I will mail it to them, sir, to you.
Okay, madam, all right.
Okay. Thank you very much, sir, investing your time in our students and our research scholars.
Right.
Your presentation was excellent, and we have got a lot of knowledge regarding hybrid fibers and the beam column sub-assemblies. Thank you very much, sir.
So I am very much thankful to Madam and Professor Kulkarni and my colleague Snehanshu Nath. I will also welcome to all the participants and also encourage to do such kind of experimental work that will have some good impact to the environment. And I am also thankful to the participants for listening and to invest your time. Thankful to the Parul University to give such kind of scope to deliver my lecture. Thanks to all the participants and the organizing members.
Thank you, sir. Thank you.